Hello, welcome back to our class of soil mechanics. Okay, we will try to make progress in the program. In this video, from this video, we will start the chapter number 4, which is about plasticity and structure of soil. Okay, so these are the points we will discuss in this chapter, from introduction, point number 1 to the point number 8, soil structure. Okay. For this precise video, we will talk about these 2 points. First, the introduction, and the second point, which is liquid limit of soil. We will see what is liquid limits soon enough. Okay, introduction then. Atterberg limit. This Atterberg is the person who worked on this limit of consistency of soil. So he proposed some limit which we will define very soon to describe the amount of water of the soil that will change the state of the soil, like from solid to plastic, for example. So these Atterberg limits are used to describe consistency of fine-grained soil. If you remember, in the previous chapter, we have talked about relative density, and we said that relative density is only about grain, like it doesn't concern fine grain. Okay, relative density doesn't concern clay, for example. It concerns only like sand, gravel, this kind of soil. So for fine grained soil, we will mainly talk about this Atterberg limit. Okay, so this limit will change with varying the moisture content in the soil. Do you remember the formula of moisture content? It's weight of water divided by weight of soil, grain soil particle. Solid part of the soil, because soil has 3 parts, 3 phases: solid, liquid, which is water, and gas, which is air. So weight of water divided by weight of the solid part of soil, that is the moisture content. So this limit, this Atterberg limit, they include the shrinkage limit, like solid to semi-solid. So if you have a solid soil, like clay, solid, if you add water, at a certain point, this solid soil will change to semi-solid. So the limit between the solid to semi-solid is the shrinkage limit. And if you reach the semi-solid state of soil, and you keep adding water, for example, you will reach plastic state. So this limit before reaching the plastic state of the soil is called plastic limit. And we have liquid limit. That liquid limit is the limit of plastic to liquid. Okay, so it means if you have plastic state of soil and you keep adding water, at certain point, your soil will become liquid. That limit of liquid limit. here is a graph that explains what I have said in more detail. So at the beginning, we have liquid, we have solid, and if you add water, you will go to semi-solid. So the border between solid and semi-solid is called shrinkage limit. That is SL. And if you keep adding water from semi-solid to plastic, you will have another limit, plastic limit, PL. And from plastic to liquid, you will have another limit, the liquid limit. So plastic, liquid, and solid. This is, for example, the stress-strain relationship for each state. For example, between solid and semi-solid state, you can have this kind of curve between the stress and strain curve like this. So means if you apply a certain amount of stress on the soil, the corresponding strain will be like this. And as you can see, if you add more water, the stress, you will need a small stress to cause a large strain. Means the soil has lost its strength. So in this state, plastic or liquid state, the soil doesn't have any strength at all. With almost zero stress, you will have, of course, a large strain. So for those who don't understand what is stress, what is strain, we can explain that later. But this parameter called Atterberg limit, they help to categorize soil behavior and provide good information about soil characteristics. So in this chapter, we will try to explain how to determine this Atterberg limit, all of them, and how also this Atterberg limit will help us to calculate some related geotechnical parameter like activity and liquidity index. We will talk about these two later. What is activity of soil? What is liquidity index of soil? So I was talking about definition of stress and strain. This figure can give us a definition of stress. So if you have, for example, this original shape of a soil sample, okay, this soil specimen, and you have this section, A is a section of like area of this soil. The F is the force applied on that area. Okay. If you do that, what we are calling stress is just the applied force divided by this area. Okay. This is just for those who don't understand yet what is stress, what is strain. So that is stress. So stress is just force divided by area. The area on which the force is acting. And the strain is, you see, when you apply force on the soil specimen, soil sample, the soil will deform. So that deformation, this small l, divided by the original length of the soil specimen, will give you the strain. So that is the definition of strain. And now, the capacity of the soil to stand, to resist the stress. That is the strength of the soil. As you can see here, this soil, for example, when the soil have this state, the soil has larger strength, because we need a large stress to cause small strain. So means this soil is strong. But in this case, for example, you can see that the soil doesn't have any strength at all. Here is medium one, transition. The soil still has some strength, but it considerably reduced compared to the original state without soil, without water inside. Yeah, anyway, this chapter is just how to determine the liquid limit, plastic limit, shrinkage limit, these limits, in how we can use this limit to determine the activity of the soil and the liquidity index of the soil. Yeah, that is the objective of this. That are the objective of this chapter. Okay, that is the introduction. Okay, let's move to the next section, the section 2 of this chapter, which is about liquid limit. So the liquid limit is obtained by using a device. Liquid limit test device. It consists of like cup and a hard rubber base, something like that. This is the base, rubber base, and this is the cup. Sorry. So it kind of, you put the soil in this cup to do the test. We will explain how to perform this test for liquid limit. So just, and there is also a handle around here, but this is just a drawing. But you can see here, this is me when I was bachelor student. This is what I'm holding here, and this is the handle, and the cup is here, and the base is this base. Okay, so to perform the test, the soil paste is placed in the cup. You put the soil in the cup. After placing the soil in the cup, you make a groove in the center of the soil. Okay, so after making the groove now, this is, for example, a photo I took in my lab. You see how the soil is, maybe it's like clay, and it's like a paste. You put it in the cup, and you make the groove in the center of the soil. These two are the tool for making the groove. There are two types, this type and this type. Okay, so after making the groove using this tool, you then lift the cup and drop it. That will cause the flow of the soil. By doing that, this, you see the handle I am holding here. If you turn the handle like this, it will lift and drop the cup. This part will drop on the base, the rubber base. And by doing that, you will see the groove you made in the center of the soil will start closing. it will be something like that. At the beginning, you will have like something like this, making this groove. This is, for example, section view of this cup, and you can see the groove made by using this one. For example, you see 2 mm here, and these are the same 2 mm we have here. And at the top, the upper part of the groove is 11 mm, which is exactly this 11 mm we have here for this tool, 11 mm of this tool. And the height of the soil in the cups will be 8 mm. As you can see, it's same as this 8 mm here. Okay, mean this. By making the groove, the plan view of this after making groove will be like this. Okay, so this plan view, what we want, what interests us is a distance of 12.5 mm of this plan view. Okay, so the plan view is showing exactly like horizontally the groove made between the soil in the middle, in the center of the soil. And after dropping, you will see the soil flowing and closing the groove will be like this. Okay, this is section view and plan view. After dropping many times, several times, after dropping several times the cup on the hard rubber base. Okay, so what is now the liquid limit? How do we find the liquid limit? Okay, so the soil water content, moisture content required to close this distance of 12.5 mm, just this distance, along the bottom of the groove after 25 blow is defined as the liquid limit. You see, for example, this soil here, this mixture of clay with water, we can determine the water content of this soil. And you know the formula, weight of water divided by weight of solid particle. Okay, then if we use this soil, put in the cup and drop, make the groove and drop it 25 times, 25 blow, 1, 2, 3, up to 25, and the groove closes, then the amount of water in this soil is the liquid limit. This is how it works. So the liquid limit is just a water content, moisture content. That for sure, but not any water content. The water content that give a state of the soil, which state close, the groove will close after 25 drops. This is what we are looking for. So it means that for some soils, some water content, if you drop only like 10 times, it will close already. This means your soil is, there are a lot of water in, you are over the water content in the soil is too much, because you drop maybe only 10 times and it closed already. It means there are too much water in, there is too much water in your soil. So on contrary, if the soil is too dry, you will drop the cup maybe over 30 times before it closes. The growth closes. Means no much water. Soil is almost hard, almost solid. Okay, so it's very difficult to make the mix water and soil and have the water content that will close the growth at exactly 25 blows, dropping the cup 25 times. It's very difficult to obtain that at only once. So for that, people did a lot of tests. You have to do several tests before to determine this. So people did a lot of multiple tests and try to change to estimate the relationship between the water content, moisture content, and the number of blows, actually logarithmically. And they propose this kind of method. So now in the lab, people are doing this every time. You do a lot of tests, at least 3 actually. One, each point represent one test. 1 point, 2 point, 3, 4. So at least 3, and manage that the 3 points, at least one has the n higher than 25, and another one has the n value less than 25. So this water content, this vertical axis, and horizontal one is number of flows. But don't forget, here is log scale. After doing that, plotting the point, you can just draw this kind of curve. So as I was saying, at least 3 tests for the same soil are conducted at by in changing the moisture content, the water content. You change the water content and you do the test. Or sometimes you just use the same soil. At the beginning, you put too much water, and in time, the water will evaporate and the amount of water in the soil will decrease, and the soil will become like little by little solid. So during the solidification of the soil, you will have at least once the water limit you are searching for. No, at least three tests with varying the water content. So this curve, just estimation. This curve is called like flow curve. The flow, how the soil will flow to close the growth made in the center. And the water content corresponding to 25 blows give us the liquid limit, as I explained before. 25 blows. So, and you have to use the curve, the flow curve, by using the flow curve, because to get this exact point in the test is difficult, even if sometimes you can get it right. Just use the curve, the estimation curve. You see the curve is just a straight line, linear relationship. So you start from here, 25, go on the curve and project this on the vertical axis, which is water content. Okay, So in this case, we can say that the liquid limit is 42. 42% of water content give us the liquid limit of the soil. The slope of this curve, this flow curve, is defined as the flow index, which can be obtained by this formula. IF, sorry. So W1 minus W2 divided by log of N2 ratio of N2 to N1. W1 and W2 here is 2 are the water content of soil in percentage. N1 and N2 are the blow, number of blow corresponding to this W1 and W2. Here is W2, okay? It's just a mistake. So as you can see here, the W1 and W2 are exchanged so that we can obtain a positive value, because as you can see, the slope of this curve is negative. So after that, then we can say that the equation for the flow line, this line, can be obtained with this relations. Means water content is equal to minus IF. IF is the index, the slope, the flow index, log N plus C, and C is just a constant. I will just skip this figure here. We will use it again. So, US Army Corps of Engineers propose an empirical formula, which is like this, to determine the liquid limit. They say liquid limit is equal to water content corresponding Wn is water content, the factor of the number of blows, N, divided by 25, and power tangent beta. N is the number of blows, okay, N. Okay, number of blows that will close the groove. And Wn is the water content corresponding to that number of blow. The tangent B is estimated to be 0.121. But this value of tangent B is not true for all soils. Some soils, this value doesn't work. So this equation is working for N value between 20 and 30. And the formula is known as like 1-point method and is adopted by American standard. So this means that you do only the one test. By doing only one test, you can use this formula to obtain the liquid limit. Only one test, because previously, instead of doing 1, 2, 3, 4 tests before you determine your liquid limit, by using this formula, you need only one test. Only 1 point is necessary. So you put water in the soil, you know the amount of water you used, means you know the water content, and you do the test. The number of blows you obtain, if it falls between 20 and 30, then it's good. you can use this formula directly to obtain the liquid limit using the water content of the test and the number of blows you have obtained. And by using this tangent beta value of 0.121, you can obtain easily your liquid limit. And this is the value of all this part, n over 25 in power tangent b, and we said tangent b is 0.121. So according to the number of blow, this value can be used from 20 to 30. So you can use this table by knowing the water content, means the amount of water you have used, and knowing the number of blows. You can easily, just by using this table, you take this value, which will correspond to all this part of this equation, and you multiply by your water content. You will get your liquid limit. Okay. Another method used to determine this liquid limit is the fall cone method, which is adopted by British standard. That method is also another popular method using this device. So you see a cone, this is a cone, and we drop this cone in the soil sample. So the test is, in this test, the liquid limit will be defined as water content at which a standard cone, this cone, with the angle of 30 degrees and weight of 0.78 Newton, will penetrate at 20 millimeter in the soil in 5 seconds after dropping the cone. This is the drawing of this cone. We have here the soil surface is here, and this cup, this one, we have this 40 millimeter inside. We just want a penetration of 20 millimeter. You remember, as the previous method, we wanted 25 blows. Here the M is 20 millimeter penetration of this 20 millimeter D. This D from the top to the end, the head of this cone, the D need to be 20 millimeter. Of course, you already can guess that if the soil is too wet, the water is too much, the cone will penetrate too much over the 20 millimeter. And if the soil is too dry, the penetration will be less than, D will be less than 20 millimeter. So this is just about geometry of the apparatus. So how we define it? To determine the liquid limit, at least 4 or more tests are conducted, changing the water content. And if we plot the graph, it will be something like this. So penetration, the distance D, the penetration means this distance, and the water content here in y-axis. X-axis is just penetration. And the liquid limit is the one that will give us penetration of 20. So the liquid limit corresponds to the moisture content, water content, when D is 20 millimeter to So if you go here, you go up and go here, you will get the monster content. The flow index, as we defined also in the previous method, also we talked about flow index. In this method also, we can find the flow index from this graph, and the formula for this flow index is given by this formula. Is expressed in this equation. W2 minus W1 divided by log of G2 minus log of G1. Yeah. W2 and W1, 1 and 2 are monster content at the cone penetration of distance D1 and D2 respectively. So I think that is all for this part of the chapter. So see you in next video for the next part of the chapter. Thank you very much.